Hi, in this lesson we're going to look at the vector equation of a line. Now, we've already dealt with equations of straight lines on the Cartesian plane in 2 dimensions. We need to think about what this is going to look like when we're dealing with vectors. How can I describe that straight line y equals mx plus c using vectors? So, here we go. Let's take example the line y is equal to 2x plus 1. We know that it looks like that. We know that it's got a y-cut of 1 and it's got a gradient of 2 up and 1 across. That's what the rise over the run is over there. Now, this line has a direction that can be written as a vector. That vector is simply going to be this one over here, 1 across and 2 up. It's different to the way in which we define our gradient. Remember, gradient is rise over run, but vectors, we've got our top number is how much we go across, and our bottom number is how much we go up. So we just need to be careful of that. So the vector here for this line, the direction of this line, is going to be the vector 1 over 2, 1 across, 2 up. Now we need another point on the line somewhere, and we can see that the point 1, 3, that point over there, is a point that lies on the line. And we know that the direction of this line over here is given by the direction vector 1, 2. Now, if we have another point somewhere on this line, the point 3, 7, we can see that, 3, 7. Well, let's see how we can get to there. If I start off at my point 1, 3, so there's the position vector that's fixing the point 1, 3, and then I take my direction vector, we can see that there's one direction vector will get me up to the point 2, 5, and another direction vector will get me up to the point 3, 7. So I've got two lots of these vectors, 1, 2, will get me up to the point 3, 7. If I think about this another way, it's possible to go and find the point and check whether the point 1, 0, 1 is on the line. Well, we know that it's on the line. It's this point over here. It's the y-cut. Well, once again, I start off at my point 1, 3, and then to get down to the point 0, 1, I'm going to have to go in the opposite direction to the way in which this vector 1, 2 is going. Vector's going 1 across, 2 up. But I don't want to go up, I want to go down. I want to go 1 across and 2 down. And that's going to be given by this vector over here. So I'm going to take away the direction vector here, and that will get me the point 0, 1. In fact, we can check if the line 5, 11 lies on the line. Well, we start off with our position point, position vector 1, 3, and then we've got to add on a certain number of 1, 2s, direction vectors 1, 2s, to get me up to the point 5, 11. Well, I think you will most of you realize that if I go and try 4 lots of these vectors over here will get me up to the point 5, 11. And so I can see that the point 5, 11 lies on the line. It's possible to do this for any point that lies on the line. And so I'm getting a generalized form that looks like this. I've got to have my position vector, that's a point that lies on the line, and I need to have some multiple of the direction vector. So what value of lambda is needed to get to the point -1/2, 0? Well, if I go and use this format of the line over here, the position point plus a multiple of the direction vector, we just need to equate the x coordinates. So in other words, 1 plus lambda, 1 times lambda, in other words, 1 plus lambda, that should equal -1/2. In other words, lambda has to equal -3 over 2. If we try that now and see what happens if I go and put that value of -3 over 2 here into the equation, well, I get 3 plus 2 times -3 over 2, in other words, 3 minus 3, and that gives me the point 0 as expected. So yes, that point -1/2, 0 is on the line. So to generalize this, we can say in order to get the vector equation of a line, we need a point on the line, and we need a vector that is parallel to the direction of the line, or the direction vector of the line. And the equation for a line, vector equation of a line, is given like this. We use this value r instead of the value y. So we have the value r, meaning the vector equation of this line is going to be made up of a position vector and some multiple of the direction vector that goes along the line. We have seen that any straight line can be written in the form of a vector, in vector form. The vector form, though, is not unique. Not like y is equal to 2x plus 1. We could have any starting point, and we could choose any vector that's parallel to that line. So we've seen this is the vector equation for the line, given that we use the point 1, 3 and the direction vector 2, 1. However, I could have taken the point 0, 1 because that's a point that lies on the line. And I could have taken the direction vector as being 2, 4 instead of 1, 2. That's just a multiple of this thing over here. And that would have given me a vector equation that looks like this. And that's fine. There are multiple vector equations of a line. They're not unique in the same way as they are in the Cartesian situation. You can test to see whether this works with that 0.511. What value will lambda be? Well, lambda would have to be 5 over 2. If we check that out, yeah, we get the value of 11, which is the y value of that point. So it works. The vector equation is not unique. Now we can expand this out into 3 dimensions. So instead of just having a 2-dimensional point, we're now going to have a point somewhere. That's going to be the point P1, P2, P3. And we need to have a direction vector. And that direction vector is also going to have 3 parts to it, D1, D2, D3. And in order to get the vector equation of a 3-dimensional line, it's going to be written like this. R is equal to the point on the line plus some multiple of the direction vector of the line. So it's consistent with what we had in 2 dimensions. Lambda is just some scalar, a number that tells us how many multiples of the direction vector we're going to use to get to the point that we want to. We can also write in terms of I, j, and k. Once again, this first part over here, P1i plus P2j plus P3k, that's simply the point that we've got. It's those values over there multiplied by the direction vector, lambda times the direction vector, and that's going to be D1i, D2j plus D3k. Note that a quick way to tell if lines are parallel is to check their direction vectors. If the direction vectors are the same, then the lines are going to be parallel. If the direction vectors are not the same, then they won't be. So let's take a look at this. Let's see if we can get the vector equation for this line in 3 dimensions. Well, to begin with, it's always a good idea to just have a rough diagram. We know that we're wanting to get the line AB. So I need to have the direction of that vector AB. I could start at point A or I could start at point B. It doesn't really matter. I'm going to look at the direction vector AB, and that's simply going to be B minus A, work that we did earlier. And the vector equation of this line is then going to be either using the point A, so the position vector A plus a multiple of the direction vector AB, or in fact it could be the other way around. I could also have little b and the direction vector, this time not of AB but of BA. Let's just follow these through. So we find the direction vector for AB. It's going to be minus 3, 1, and 1. And then I can choose either point. In this case, we've chosen A, but we could have chosen B and that direction vector as well. That would have worked. Other possible ways that we could have done it, say we could have looked at the direction vector and taken the point B, Or we could even go on and switch this around. And so instead of having the direction vector -3, 1, 1, we could have had the direction vector 3, -1, -1. In other words, the direction vector that's going from B to A, the other way around. And again, I can use either that point or this point because they're points that lie on the line. Once again, let's stress this point. Vector equation is not unique. So here are some questions. Find the vector equation of the line passing through the point 1, 2, 5 and parallel to the direction vector 2i, 3j plus k. Well, we know that we've got the direction vector. We know that we have a position vector. So we've got the two things that we need. All we have to do is plug it into this formula of r is equal to point plus lambda times some position vector, direction vector rather. Write down the direction vector of the line for this line over here, and does the line pass through the y-axis? Well, the direction vector, that's fairly straightforward. We know the direction vector is just this multiple of mu that we got over there. Now, if it passes through the y-axis, then we know there must be a coordinate on the y-axis that's going to have an x-coordinate 0, a z-coordinate 0, and a value for y. So in other words, this equation would have to equal that point if that if the line were to pass through the y-axis. So we now need to equate the x's. Get that mu is equal to 1. We equate the z coordinates. We get that mu is equal to -2/3. So here I've got different values for mu, and so this clearly is not consistent. And so there's no single value for mu that will work for this particular formula. And so we know that the line does not pass through the y-axis. Now, while we're dealing with vector equations of lines, let's also talk about the angle between lines. We need to do a quick recap here of work that we did the other day in terms of the scalar product. So just very quickly, if you've got two vectors, A and B, the angle between them is simply going to be the dot product of A and B divided by the magnitude of A and the magnitude of B. So that should be fresh in your mind because it's what we did 2 days ago. Right, let's find the angle between these two lines. So here we have line 1, which has a point on it at the point 2, 3, -1, and a direction vector that looks like this, 4, 1, 3. And then line 2, which passes through this point and has a direction vector of 3, -2, 5. The key thing that we're going to have here, we're going to look at here, is the direction vectors. So first of all, we need to look at what the scalar product of that is. So in other words, I'm going to multiply my x components, my y components, my z components, and then add them together. And that gives me 25. I need to find the magnitude of each. So the magnitude of the first one is square root of, what is this, 16, 17, 26, I think. And magnitude of the second one, which is what, 9 and 4 is 13 and 25 makes 38. So there we have the scalar product. Here we have the magnitudes of each of these. And so if I want to work out the angle, I can simply say cos theta is going to be A dot B over mag A mag B. And that gives me a ratio of 0.795. And that means I've got an angle of theta being 37.3 degrees. Now you may well remember that when we worked with vectors last year, one of the key things that you dealt with was perpendicular lines and how you could show that lines were perpendicular. If you remember, lines are perpendicular if their scalar product is 0. So let's look at an example of this. So we have 2 points, A and B, and we have a line perpendicular and this line is perpendicular to the vector 3i pj plus 3k. We need to find the value of p. Well, first of all, it would be worthwhile getting the direction of the vector that passes through a and b. It's simply going to be b minus a, and that comes up as the direction vector 1 minus 6, 3. The equation of the line through a and b is going to be given by some point a and multiples of the direction vector. So I'm going to choose the point 251, where's our direction vector. Now, we say that this line over here is perpendicular to this line over here. In other words, their dot product, their scalar product, should be 0. So if I took the direction vector of this line, which is the line 1 minus 3, 6, and the direction vector of, or this as a direction vector, which is going to be 3p and k, 3p and 3, I just need to take their dot product. Because it says they are perpendicular, I know that the dot product would have to equal 0. And so I can now make a little equation there, because that times that, plus that times that, plus that times that has to give me 0. And if I solve that out, I'm going to get that p is equal to 2. And so I've been able to solve that problem. Right, now is the time for you to go and do some practice on this from your textbook. Hope this helps. Goodbye.